Most of us started playing with paint when we were little kids. As artists, you've probably used a variety of color media, whether it's watercolor, acrylics, oils, maybe pastels or colored pencils. By now, the process of mixing colors to produce new colors has become second nature. We all know that blue and yellow make green, red and blue make purple, red and yellow make orange, and so on. But creating colors on the computer is a very different process and not nearly as intuitive. Over the next two lectures, I'm going to talk about what color is and how it's created digitally. We'll discuss how monitors create color, how the computer stores color information, and how color images are printed on paper. In order to understand how digital images are created and how computers store and display color, obviously we have to understand what color is first. Let's start with a little analogy. You've probably all heard the old philosophical question, if a tree falls in the woods and no one's there to hear it, does it make a sound? The answer to this question is really quite simple. It depends on how you define sound. On one hand, sound is a physical phenomenon. It is energy that travels in waves through the air or through water or through some other medium. On the other hand, sound is a human experience. Those energy waves reach the tympanic membrane or eardrum of a person, causes the eardrum to vibrate, which in turn causes bones in the middle ear cavity to vibrate, and eventually that vibration is transferred to an organ called the cochlea in the inner ear. The cochlea translates the mechanical energy, the vibration, into electrical signals which are sent to the brain, and the brain interprets that sensation as sound. So sound is a physical phenomenon, the propagation of energy waves, but it's also the human experience of those sound waves. Most people these days tend to prefer the latter definition, that it's a human experience of a physical phenomenon. Therefore, the answer to that philosophical question is that if there's no one around to hear the sound, then it does not make a sound. The same is true for color. Color is a physical phenomenon, but this physical phenomenon interacts with the human eye to create a human experience. Let's talk about this in a little bit more detail. In order to talk about color, you first have to understand what light is. Visible light, in other words, the light that we can see, that we can perceive, is one form of electromagnetic radiation. Electromagnetic radiation is a form of energy that travels in waves. There are many different types of electromagnetic radiation, all of which are distinguished by their wavelength, which is the distance between the crests or the peaks of successive waves. So you'll have a series of waves that are traveling in a given direction, and the distance between the peaks or the crests of those waves is the wavelength of this electromagnetic radiation. Visible light, the light that we can see, represents a small portion of the variety or the range of different types of electromagnetic radiation. Visible light is electromagnetic radiation that has wavelengths ranging from about 400 nanometers, that would be violet light, up to about 700 nanometers in length, that would be red light. So all of the wavelengths of electromagnetic radiation that fall within that range from about 400 to 700 nanometers is what we call the visible spectrum. These are all of the different forms of visible light. On the left, you see a comparison of long wavelength electromagnetic radiation with shorter wavelength electromagnetic radiation. So the wavy lines simply represent pulses of energy that travel in a wave form, and the distance from one peak to another is known as the wavelength. On the right-hand side, you can see all of the other types of electromagnetic radiation arranged in order by increasing wavelength. Electromagnetic radiation with extremely small wavelengths are things like gamma rays and X-rays and even ultraviolet light. Then you get into that range of visible light from about 400 nanometers up to about 700 nanometers of wavelength. And then things that have longer waves than that are the infrared radiation, radio waves, TV and FM broadcasts, AM radio, and long-wave radio broadcasts. So the human eye is only sensitive to that rather small portion of electromagnetic radiation that falls in that fairly small range from 400 to 700 nanometers in wavelength. The human eye cannot see any of those other forms of electromagnetic radiation. In order to emphasize the point that color is a human experience, I should point out that other animals see color very differently than we do. Dogs and cats, as it turns out, have very poor color vision. They're almost completely colorblind. Marine mammals, such as dolphins and whales, are completely colorblind. And this is probably due to the fact that very little light reaches down into the depths of the ocean, and you can make out shapes, but you can't see color at that depth. So there's really no reason why those animals would have color vision. On the other hand, there are many animals that have much better color vision than we do. It turns out that most birds, even some fish, even certain invertebrates like octopus, see color better than we do. Their eyes are sensitive to more different wavelengths of light, and therefore they can see colors that we can't see. Many insects, particularly bees, can see well into the ultraviolet range, so their eyes are actually sensitive to ultraviolet light, which is completely invisible to the human eye. And what you're seeing here are photographs of flowers showing what the human would see at the top, where these flowers just seem to be, uniform yellow color. But if you illuminate these flowers under ultraviolet light, you can see what the bee is able to sense, and you find that there are these very distinctive patterns that are only visible in the ultraviolet range. In many cases, these patterns seem to be almost like little landing strips, guiding bees into the center of the flower in order to pollinate the flowers. So how do we actually see color? I'm sure you all know that light enters the eye and strikes a membrane called the retina, which lines the inside of the eyeball. Deep within the retina are groups of cells called rods and cones, which are sensitive to light. They actually absorb photons from light and translate that light energy into electrical signals, which are then sent to the brain for processing. The brain then interprets that sensation as light and color. On the right, you can see a close-up view of the layer of rod and cone cells, the rods shown in yellow and the cones shown in blue. Rod cells are sensitive to many, many different wavelengths of light, but they can't tell one wavelength from the other. All they know is that it's either light or dark. So the rod cells are very sensitive to changes in brightness, and they can make out objects, but if you only had rod cells, you would be colorblind. You wouldn't be able to distinguish one color from another. The cone cells, on the other hand, are sensitive to very specific wavelengths of light. It turns out that some cones are sensitive to red light, some are sensitive to green light, and some are more sensitive to blue light. And so when these different wavelengths of light hit the eye, they stimulate different groups of cone cells, and that's what allows you to distinguish one wavelength or one color of light from another. In the bottom left of this slide is a graph that represents how these different cone cells respond to different wavelengths of visible light. So you'll notice the blue line shows how a certain set of cone cells responds to certain wavelengths of light. And you can see from the width of that line that this group of cone cells can detect a range of different wavelengths, but it's particularly sensitive to light at about 420 nanometers in wavelength, meaning that this group of cone cells is particularly sensitive to blue light. There's another group of cones that also, again, detect a range of different wavelengths, but are particularly sensitive to green light at about 530 nanometers, and another group of cones that's particularly sensitive to red light at about 560 to 570 nanometers in wavelength. So these three different cone cells are particularly sensitive to red, green, and blue light. But what happens if a wavelength of light enters the eye that doesn't fall right at one of these peaks? So for example, let's say that light entered the eye at a wavelength of approximately 470 nanometers. That falls right in between that blue peak of 420 and the green peak of 534. This type of light would stimulate the blue and green cone receptors equally, and the brain would interpret this as a light bluish-green color that we call cyan. If you look at the right side of the slide, you'll see the three overlapping circles of red, green, and blue light. And you'll see that when red and green light combine, the eye perceives that as this very light bluish-green called cyan. Similarly, if red and blue cone cells are stimulated, that combination of wavelengths of light is perceived as a light purplish-red color called magenta. The one that most students have the most difficulty grasping is that if you stimulate red and green cone receptors in the eye, the brain actually interprets this as the color yellow. And so a combination of red and green light actually makes yellow light, or at least that's what the brain perceives as yellow light. This is a little difficult to accept because it doesn't work this way with paints. You mix red and green paint, you get an ugly mess. These three colors, red, green, and blue, are referred to as the additive primaries. They're called primary colors because you can't create either of these colors from any other color. However, you can combine these three to create new colors. As we've already discussed, green and blue can be combined to make this cyan color. Red and blue can be combined to make magenta, and red and green can be combined to make yellow. The reason that these are called additive is that whenever you mix two colors of light together, you are adding more light, and therefore the resulting color is always lighter or brighter than either of the primary colors was by itself. So again, if you mix red and green light, the result is going to be a lighter or brighter color than either red or green by itself. The three additive primary colors, red, green, and blue, can be mixed together in different proportions to create all of the other colors in the visible spectrum. And so it's possible to create all of the different colors that we see in our surroundings by mixing different amounts of red, green, and blue light. Also notice at the center where all three types of light overlap, there's a white area. That's because when you combine equal amounts of red, green, and blue light, the eye perceives this as white light. Now that we understand how the human eye perceives light and color, let's talk about how your computer actually generates the color that you see on screen. Dating back to the 1940s, scientists had developed technology that allowed the recording, the transmission, and display of color images electronically. Color televisions became commercially available in the 1950s, although very few networks were broadcasting in color at that time. They were still broadcasting just a black and white signal. By the 1960s, though, color television had become widespread. All of the major networks were broadcasting in color. And by the 1970s, color TV was the norm. At about that same time, beginning in the 1970s and continuing into the 1980s, color television technology was adapted to create computer monitors. A color television, or a computer monitor, emits three wavelengths of visible light: red, green, and blue light, the three additive primaries. And a color TV, or a computer monitor, can create all of the different colors in the visible spectrum by simply varying the intensity of those three additive primary colors. Now, there are a couple of different technologies for doing this. The original televisions and original computer monitors all used something called a cathode ray tube, which was a very large, heavy vacuum tube with a large magnet near the back of it. The tube generated beams of electrons that shined forward onto the inside of the screen. The magnet was there to simply focus the beams of electrons. The electron beams, in turn, would strike substances known as phosphors on the screen, and this would cause the phosphors to glow red, green, or blue. And by changing the intensity of the electron beam, you could change the relative amounts of red, green, and blue light that were displayed to create the colors of the visible spectrum. More recently, cathode ray tubes have fallen out of favor just because they're so big and heavy, and most televisions and computer monitors now are based on something called a liquid crystal display, or LCD screen. This consists of crystals which glow in the presence of an electric current. So the computer sends electric current to the screen, it stimulates crystals to glow either red, green, or blue, and by varying the amount that the crystals glow, you can vary the amount of red, green, and blue light to create the colors of the visible spectrum. Now, color televisions aren't perfect, and computer monitors aren't perfect. In theory, these RGB devices, these red, green, blue devices, could produce all of the colors in the visible spectrum. But because of limitations in technology, they actually cannot reproduce all of the colors in the visible spectrum. This has led to the development of a concept known as a gamut. Imagine that that colored circle represents all of the possible colors that exist in the visible spectrum. The black line represents the group of colors that can be displayed by any given RGB device. So for any particular color television or color monitor, you could draw a black line like this that shows which of the available colors this particular device can actually reproduce. So we call that the RGB gamut. And that will become important later when we talk about color calibration. So now we know how the eye perceives color, and we also know how computers can display information on a monitor. But how does the computer actually store that color information? In other words, when you save a digital graphic, how does the computer remember what the colors are that were present in that particular image? In order to understand that, you have to understand a little bit about how computers store all sorts of information. All digital information is stored in what's called binary format. The word binary actually comes from the Latin, and it means 2 by 2, or in groups of 2. And what this means is it's actually a type of math that uses just 2 values, ones and zeros. So all data in a digital file is stored by saving just long strings of ones and zeros. The smallest unit of data in any digital file is what we call a bit. A bit is literally a bit of data that can exist in 2 different states. We could say that the bit is turned on. In other words, the bit is occupied by the digit 1, or we could say that the bit is turned off, in which case the bit is occupied by the digit 0. So each bit of information can exist in just these 2 states, either a 1 or a 0, on or off. There are other units of measurement for computer storage. A group of 8 bits makes up something called a byte. 1024 bytes makes up a kilobyte. 1024 kilobytes makes up a megabyte, 1024 megabytes makes up a gigabyte, and so on with terabytes and other measures of computer storage. When you create a raster image, the computer has to set aside a certain number of bits of data to remember the value or the color of each pixel. Let's consider an example. There's a type of image known as a bitmap. A bitmap is a raster image where there is only 1 bit of data assigned to remember the value of each pixel. So for each pixel in the image, there's only 1 bit of data that is assigned to remember what the value of that pixel should be. If that bit is turned on, in other words, if that bit is occupied by the digit 1, then the pixel appears white on screen. If that same bit of data is turned off, in other words, if it's occupied by 0, the pixel appears black on screen. You can think of this like a light switch that turns on a light bulb in a dark room. When the light switch is in the on position, the light turns on and the room appears white. When the light switch is in the off position, the light is off and the room appears black. So in a bitmap image, each pixel can have only 2 values. The pixel can either be solid white or solid black. Nothing in between. It can't be gray, it can't be a color. These were among the earliest types of digital images because they are very simple and they require very little memory because you're only assigning 1 bit of data to each pixel. But bitmaps are still widely used in certain very specific situations. For example, saving black and white line art. If you wanted to scan some pen and ink work or some scratchboard or stippled work, scanning any kind of high contrast black and white line art, you would use bitmap as the method for saving those images. Now, one word of caution, don't confuse a bitmap raster image with something called the Windows BMP format. BMP in this case is short for the word bitmap, but these are actually 2 completely different things. In an earlier lecture, we talked about creating a new file in a raster image program like Photoshop. Whenever you create a new file, you have to specify the physical dimensions of the image, the height and width in inches or some other unit of measure. You also have to specify the resolution, typically expressed in pixels per inch. And as you see here, you also have to specify the color mode. The color mode refers to how many bits of data have been assigned to remember the value of each pixel in this image. And as you can see in this example, I've selected the bitmap format, and right next to it, it says 1 bit, meaning that there is 1 bit of data assigned to remember the value of each of the pixels in this image. There are several other color modes that you could choose. One of these would be grayscale. A grayscale is an image that includes white and black, as well as some intermediate shades of gray. In order to create those intermediate shades of gray, the image has to assign additional bits of data to remember the value of each pixel. Let's consider a hypothetical grayscale image. I say hypothetical because this is not something that you would ever find in any graphics software, but I'm just offering this as an example to help you understand how this works. Let's pretend that you could create a raster image where there are 2 bits of data set aside to remember the value of each pixel. In this type of image, if both bits were turned on, in other words, both bits were occupied by the digit 1, the pixel would be pure white. If both bits of data were turned off, in other words, occupied by zeros, the pixel would be black. Going back to the analogy of the room with a light bulb, you can imagine a room that has 2 light bulbs in it. If both lights are turned on, the room appears white. If both lights are off, the room appears black. But there are combinations of bits, or combinations of light bulbs, that will produce different intermediate shades of gray. So for example, a 1 and a 0 might produce a light gray, whereas a 0 and a 1 might produce a dark gray. So those 2 different combinations actually produce different values of gray. So as you can see in this particular example, each pixel can have a total of 4 different values: black, white, light gray, dark, 4 different values. There's a simple mathematical formula that allows you to determine how many different values can exist in each pixel by simply knowing the number of bits that are assigned to that pixel. The expression is as follows: the number of values equals 2 raised to the n power, where n is the number of bits. So in this example, n equals 2, because we have 2 bits of data per pixel. So the total number of possible values is 2 squared, or 4. Now remember, that was just a hypothetical example. There is no raster software anywhere that will allow you to create a grayscale image with only 2 bits of data per pixel. In the real world, a grayscale image typically has 8 bits of data set aside to remember the value of each pixel. Once again, if all of the bits are turned on, the pixel is white. If all of the bits are turned off, the pixel is black. And then there are many different combinations of those bits that can be in either the on or off position to give a variety of intermediate shades of gray. Using that mathematical formula, we take the number 2 and raise it to the 8th power, and we see that this results in 256 different possible values for each pixel. So if we do that math very quickly, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128, times 2 is 256. So that was 2 multiplied by itself 8 times to yield 256 different values. Those values include pure black, pure white, and 254 intermediate shades of gray between black and white. It turns out that this is actually more gray values than the human eye can differentiate. So what about storing color information? By far the most common type of color image is one that is stored in RGB color, where RGB stands for red, green, and blue. In an RGB color image, there are 8 bits of data per pixel for each of the 3 colors. So there are 8 bits of data for the red, 8 bits of data for the green, and 8 bits of data for the blue information. It's almost like 3 grayscale images combined, but instead of grayscale, you have a range of values of red, a range of values of green, and a range of values of blue. And again, because there are 8 bits assigned to each of those color channels, there are 256 different levels of red, 256 levels of green, and 256 levels of blue. These different levels of red, green, and blue can be combined to produce a total of 16.7 million different color combinations. If you really want to do the math, you can verify this yourself. We've got 8 bits of data for the red, 8 for the green, and 8 for the blue. That adds up to a total of 24 bits of data assigned to each pixel. Using the formula from before, 2 raised to the 24th power is 16.7 million different values that can exist in each of the pixels. Because there are 24 bits of data assigned to each pixel, this is sometimes referred to as 24-bit color. RGB images frequently have an additional 8 bits of data that is assigned to what's known as an alpha channel. The alpha channel controls things like the transparency of the pixel. Or in Photoshop, you can create masks so that some pixels are visible and some are hidden. or you can save selections. The 8 bits of data in the alpha channel are used to remember those different types of information. So RGB color images may not be 24 bits, they may actually be 32 bits. 24 bits of color information plus an additional 8-bit alpha channel assigned to each and every pixel in the image. This slide shows how you would choose different RGB values in all of the Adobe graphics software. Notice that each color has a little slider that allows you to increase or decrease the amount of red, green, or blue light. And there's also a space where you can enter the same information numerically. Notice in the upper left that the red, green, and blue sliders are all set to 0, meaning that the red, green, and blue light is completely turned off, and therefore any object that you created with this color would be pure black. It would be the complete absence of light or color. In the middle example on the top row, the red has been turned all the way up to 255, so that's pure red. At the right, the red has been turned back down to 0, and the green has been moved all the way up to a value of 255, so this would be a pure green object or a pure green pixel. And finally, in the bottom left, the red and green are set to 0, but the blue is turned all the way up. So you can see how easy it is to specify red, green, and blue. In the bottom center, both the green and blue sliders have been pushed all the way up to their maximum values of 255, and you can see how this produces that light bluish green color called cyan. So varying the position of these sliders, or varying the numerical values of red, green, and blue, allows you to produce a whole range of colors, more or less all of the colors in the visible spectrum. In the bottom right, you see what happens if you set red, green, and blue all to their maximum values of 255. This produces pure white light. You're combining equal amounts of red, green, and blue at full intensity. The eye perceives this as white. So we've talked a little bit about how computers display color information on a monitor. We've also talked about how computers store color information in a digital file. When you save a digital file, you're saving all of the bits of data, all of those ones and zeros that define the colors of individual pixels or objects. To view that file, the computer reads the numerical data that's stored within the file and translates those numerical values into voltage, which is sent to the monitor so that the image appears on screen. Unfortunately, every monitor behaves a little differently, so that the same digital file might look very different on different computers. You can see this for yourself if you go to one of those big box stores and look at the display of all of the televisions on the wall. Even though all of the TVs may be showing the same program, in other words, all of the TVs are displaying the same data, they may look very, very different. The same is true of computer monitors. Each one is going to look a little bit different from the one next to it. Similarly, when you print that file, you are translating the numerical values stored within the digital file into some sort of ink or toner that's applied to paper. And just like monitors, all printers are a little bit different. Even two printers of the same model, the same brand, may print a little bit differently. So this digital image that you've created may look different on different printers, and the image that you print may look very different from what you see on screen when you create the image. So what I'm trying to point out here is that every time you view a digital image on screen, or every time you generate a print of that image, you are seeing an interpretation of the numerical values that are stored within that file. The only thing that remains consistent when you move that image from one computer to another, or when you print the image, the only thing that remains consistent are the numerical values that are stored within that digital file. I like to say that the real image is the numerical values stored within the file. The image you see on screen is just one interpretation of that reality. The image that you print is just another interpretation of that reality. The only reality is the numerical values stored in the file. So why is this important to understand? Well, let's say that you are creating an image on a computer and it looks great on the screen. As you create the image, you're constantly looking at the screen to see what it is you're creating. But then you save that file and you move the file to a different computer, and now all of a sudden when you open that file, it looks terrible on screen. The tendency is to blame the second computer. The image looked great on screen when you initially created it, so why does it look so bad on this other computer? The problem is you really don't know which computer to blame. It's just as likely that the monitor on the first computer was out of whack, and even though you were creating something that appeared very good on screen, the numerical values that you were saving into the file were actually not very good. You were creating ugly colors, for example, but because the monitor was out of whack, it displayed those ugly colors in a very pleasing way on screen. You then move the file to a different computer. It may be that the second computer actually was giving you a more accurate representation, a more accurate interpretation of the values stored in your digital file. So you may have created an ugly image all along, you just needed to be on a better computer to see that. Similarly, you might create an image that looks beautiful on screen, but then you go to print the image and the print looks terrible. Once again, you have no way of knowing if the computer that you created the image on was giving you an accurate representation and the printer is doing a bad job of printing the file, or perhaps the monitor you were looking at initially was out of whack and you were really creating a file with ugly colors, and the printer is actually doing a better job of interpreting those numerical values. You have no way of knowing if the image you are seeing on screen is accurate or if the print is a more accurate representation of that digital file. Now, this was much less of a problem in the old days, where computers were used simply to reproduce and print traditional artwork. In those days, you always had the original traditional artwork to refer back to as the reality. You always had a real image to consult to see what the colors were really supposed to look like. This graphic explains the process of scanning and printing a traditional image. So you start on the left with an original piece of artwork, a painting, a drawing, something like that. You could scan that piece of artwork and generate a set of film negatives. We'll talk more about this in another lecture, but you need to create film negatives, which you can then use to create plates, which go onto a printing press in order to create the printed image. You can also use film negatives to create something called a contact proof, which was a very high quality type of print that's made directly from the film negatives to show you what the image is going to look like before you print it. When you look at that proof, or when you look at the final printed image, you can always compare those back to the original piece of artwork to make sure that the colors match correctly. So you always had that original real image to refer to make sure that your digital images were accurate. Unfortunately, in these days of creating images digitally from scratch, you never have that real traditional image to refer to. Everything you see is always an interpretation of the numerical values that are stored within the digital file. So in this graphic, what we're seeing is the digital file represented by that page with all the ones and zeros. That's the only thing that is real and the only thing that remains consistent throughout the whole process. Even as you are creating that digital file initially, you are relying on your monitor to show you an accurate interpretation of the values that are stored within that file. And if your monitor is out of whack, it may actually be showing you something that's very different from the numerical values in the file. Then when you go to print the file, the printer creates a different interpretation of the numerical values within that file. And here in the top right, you can see that you can print the file directly to your own desktop color printer, your own inkjet or color laser printer. That's one interpretation of the file. You can also take that digital file and print it directly to printing plates that are used on a printing press and generate a different printed image. But when you see those printed images in the end, you have no way of knowing if those images are an accurate representation of the numerical values in that digital file. You can compare the printed image to the image that you see on screen, but again, all of those things are different interpretations of the digital file. You never really know for sure what numerical values are stored in the digital file. The only way to control this process and guarantee that what you see on screen and what you see in print are accurate translations of the digital file is to properly calibrate all of your equipment. You need to calibrate your monitor so that you can trust that what you see on the monitor is a truly accurate representation of the digital file. And you also have to calibrate printers to make sure that the printers are also accurately translating the numerical values in that digital file. Now, we won't talk about how to calibrate printers in this class. Since you are all training to be professional medical illustrators, we're going to assume that you will send your final digital files to a client who is responsible for getting the images printed. Therefore, it's up to the client and the printers that they work with to guarantee that their printing equipment is properly calibrated. So you typically don't have to worry about that end of the process. However, we will talk quite a bit about calibrating your monitor. I'll actually demonstrate the process in class. This is critical because as you're creating that image, you need to trust what you see on screen. You need to know that the image you see on screen is an accurate representation of the numerical values that you are inputting into that digital file. This way you know when you send that digital file off to a client that they're getting a good quality product. And when they print that file on properly calibrated printing equipment, they're going to get a good looking print that looks exactly like what you saw on screen when you initially created the file.